Okay, so let's talk about flow maps, which are a nice way of thinking about the exact solutions as a means of comparing them with numerical methods. So the group of flow maps. All right, so let's consider a autonomous differential equation. Okay, what that means then is that the vector field does not explicitly depend on time. It's easy to convince yourself that any non-autonomous differential equation can be converted into an autonomous one by augmenting the configuration space. So any sort of non-autonomous ODE, which basically means that the vector field again is explicitly time dependent. So let's say y dot is equal to f of y and t, right, can be converted into an autonomous one by introducing an augmented variable. Let's just call that z, which is y and t. Okay, and then in this augmented variable, the differential equation looks like z dot is equal to f of z and 1. Okay, so then basically without loss of generality, we can look at autonomous ODEs because they're a much more natural setting for looking at flow maps. So for a fixed time, say t, right, we can consider the following map. Okay, so what this map does is, so this map basically takes the initial point y0 and gives you the solution at some later time. So it's y of t with the proviso that this y is the solution of the differential of the initial value problem. Which says that y at time 0 is y0, and then y dot is equal to f of y. Okay, so this thing is what we call the flow map. Which takes the starting point of a trajectory to the endpoint. Okay, so it's a way to, again, map initial data. It's like to the solution at some later time. Okay. All right, so let's look at a few examples of flow maps. So the first one is for the simple linear scalar differential equation. X dot is equal to r of x, right, which is just exponential growth. Okay. then you can check that what the flow map does to some initial data is that it takes the exponential of r times t applied to the initial data y0. Okay. And the second example was what happens if you have the harmonic oscillator. So x dot is equal to u, then u dot is equal to minus omega squared x. All right, so this is harmonic oscillator. Okay, and the flow map for this depends on the initial data, which is both position and velocity. Okay, and this is going to be the cosine of omega t, 1 over omega sine omega t minus omega sine omega t, and then cosine omega t applied to the initial data x and u. So both of these equations, it's like are examples of a system of linear differential equations. So let's ask, well, what happens more generally speaking. So for any linear ODE, okay, of the form, say I'm going to think of y as a vector now, and its time derivative is some matrix A applied to that vector, then the flow map is given by following. So it's given by what is called the matrix exponential. Okay, so the flow map applied to some initial data y, okay, is going to be the matrix exponential of t times the matrix A applied to the vector y, where you define this matrix exponential e to the ta, okay, using a series expansion. So I equals 0 to infinity of ta to the I-th power divided by I factorial. So this is, of course, the usual power series. It's like for the exponential, but I'm going to interpret this not at the level of scalar parameters, but of matrix value parameters. So in order to do that, I need to just remind you that a to the 0th power is just the identity matrix. Okay, so this is the matrix exponential. And you can check that this is a well-defined thing. It's like the series converges, that it's a bounded operator, it's like, and good things like that. Okay, so let's just stop for a second.